All right, so like Klaas said, I'm a trained architect, and I don't work at all in the field. I'll give you some info on how this went. I'm fascinated by data all my life. When I was a kid, I tried to get data on all kinds of devices and technology, or I tried to play with technology in general, but this one is particularly fascinating in the view of data because it's actually a simple process. You put data in an image, that image gets transmitted, and the top pixels of that image contain a lot more than the moving image. It's the teletext, it's gone, it's dead. It no longer exists. It's been replaced by more interactive forms of transferring data. But still, this line of pixels on the top of the screen was translated in this image. So I find that very fascinating. And I always found it very fascinating, these kinds of technologies, how data can change into form because of a process. So right after I studied architecture, yes, I started working for an architect, and I started working for Wim Delvoye, and I made these Gothic structures. These are steel beams, structural ornament, if you want, or ornamental structure, because it was a combination of, well, reverse engineering the Gothic shape into a steel form that could support the structure. But this is a very complex structure, as you might see. It's not like the Concorde, like we saw yesterday, or the Eiffel Tower, of course. It's only 9 meters high, or in its biggest form, it was like 16 meters high. But there was a need to create a database pipeline to get all this going well, because we started with little objects, and this grew bigger and bigger and bigger until we had like a tower of 11,000 different pieces. So you could say it's Gothic data farming, but eventually, after some years of evolving away from architecture and moving more into software engineering, I end up at IMEC. We're actually quite good at data farming. We have, for example, our City of Things platform, which is an IoT reference lab. We do both testing with people and with technology. We test technology, but we also test if people want to use it. So it's a large-scale, real-life smart city environment. To build this, we use a couple of our core technologies. So you have the CMOS technologies. So actually, we built microchips. That's where IMEC started. And then we started building better sensors. Now we're also making very flexible technology like printed electronics, RFID tags, even displays, small processors that are very, very cheap to produce and can literally be printed on things. We combine this with digital technology platforms for networking, data privacy, security, and data science. I make use of all this infrastructure for a lab. This is it's very hard to show a black box. So, well, I have this black box. It's my lab. It has, among other things, 25 kilowatts of speakers, with which we can do wave field synthesis. But it also has sensors, so we can capture the real context. We know movements of the people. We know where they're looking at, etc. So we can create a virtual context out of the data we capture. And eventually, we blend computed and the real worlds, so data fusion of both worlds. So for some reason, this matches really good with something else I do. I make music and I perform in a live coding band. Live coding, it's done at a REPL. A REPL stands for read, eval, print, and loop. It's a very important concept in if you want to go and explore data, if you ask me. So you get to interact with the computer at a very close level. So you interact with the process, you interact with the data. The goal is, of course, to fuse with the computer, but that's not possible today. Why are we here today? Well, we're here to talk about this, data farming and humanizing digital reality. So I come from a field of interpreting data and visualizing data and working with data. And we do this for the sake of understanding the data. I'm not saying it never happens, but the output is not necessarily aesthetic, or it does not need to be aesthetic. It's not architecture or art. We just try to make sense of the data. This record cover is Brian Eno, Music for Airports. It's actually the backside. But what's interesting is that all 4 songs, have patterns that describe the music. They are a visualization of the scores of the music. And for me, this is, this was the first time I saw, oh yeah, you can do beautiful things with data. This record is from 1973 or something, way before I was born. But it's an analog visualization of music. I love it, and the way it can communicate about the data inside is also very interesting. Good. So I want to first get more clear vision on what data exactly is. So this is a single data point, or actually it's two. It's 2 bits, a bit that is on and a bit that is off. Whether it's real or virtual, it doesn't really matter. But this is let's say, the single data point. It doesn't mean a thing if you don't put it into context. I'm referring again to the context I was talking about earlier. You need to see this in the bigger picture. Try and move your head like this if you don't see what it means. But it's a Jacquard pattern. It steers knitting machines. It's very simple. But the way but we now added more data points and put them together in a certain group makes it clear that how we should interpret it. Okay, so computers are really good at eating data. They eat chess players for breakfast. Here in 1996, I think, Kasparov was beaten by a computer. This computer could only count really fast and really long, and so it wasn't really an intelligent computer. So Kasparov was beaten by a machine that just could read really fast from a long table of pre-calculated moves. So yeah, we could say the raw power outsmarted intelligence, but what people always forget to say when they say, oh yeah, Deep Blue beat Kasparov already in 1996, is that a mediocre chess player combined with a mediocre chess computer can beat Deep Blue anytime. So it's not on how you, or how fast, or how much data you can process, but it's also on how you do it. So you need to combine this with some form of intelligence. And of course the data context. This is Mr. Jacquard, whose invention was really fundamental in computing, I think. By the way, the knitters were not happy with this person. They tried to abolish his invention. They wanted to do the work themselves. Okay, I'm gonna apply this on a use case. This is an installation. It's a data visualization installation where I work together with Luc Deleu, which is a Belgian artist and architect. And he's been busy for the past 40 years, I think, with indexing everything that surrounds us. So here you see pictures of traffic signs, football fields, swimming pools, schools, cars, everything. And he did this in an old-fashioned analog way. This is actually a Word document. So the data was really captured inside. Yeah, paper is almost better than a Word document. We wanted to cultivate this data. So we wanted to grow something out of this Word document. And so I'll zoom in. Oh. I'll zoom in a bit. So that's the kind of data in the document. It's very analog. It's an Excel sheet with manually colored fields and everything. And we tried to augment it by making it interactive. So the installation you saw was asking visitors of the exhibition to categorize objects. For example, the stratovolcano is this smaller or bigger than a canyon or a waterfall or a spring. So you could drag these in an order. So, and we did this with all of the data and all the people that passed. We had like 4,000 people in a couple of days passing the exhibition and adding the data. So eventually we were able to translate this Excel document into an explorable data visualization, where we could do clustering, where we could visualize all kinds of patterns that emerged. So the key was making it interactive. And because we eventually were able to make it interactive, we could also, well, the dream of Luc Deleu and his team was to shape the ultimate city out of it. And this is actually a very early version, but it's a sort of building block that can capture all the needs that he extracted out of that data, and this is generated then from this data. So that is how to cultivate data, but the process here is not explained very well. So I'm going to do a little contest here. Humans versus robots. You are the humans. And do you know what this is? Maybe just keep it inside your head, what you think it is. There's at least 3 possible answers. Might be more. I'm going to tell you what a computer thinks this is, because I fed it into a deep learning network, the Deep Dream generator, and the computer thinks it's a weird hybrid of animals. We see traces of dog in there, we see traces of fish and birds and whatnot. Of course, the computer was trained to recognize animals. I don't know what you recognized. People could say it's an ink stain on paper. By the way, it was the Rorschach test, if you didn't know, or one of the plates of the Rorschach test. But the thing is, a 19th century psychologist would really classify the computer as a psychopath. So we need to be careful with yeah, how how we train our computers. Suppose they survive us and then they depart from human society somewhere at some point, and then at a later point we peacefully come together again. What will we think of them if we haven't trained them correctly in the past? Okay. But it's an interpretation versus perception. If you thought, yeah, that was a Rorschach test, and you didn't think of, oh, it might be a butterfly, or maybe it's, I don't know, a bat, or something completely different. Because if you thought of something completely different, that just means you have a good associative brain, which is actually something very good, and computers are actually very bad at it. Because, really, the things it recognized, it was trained to recognize it, the shapes. I don't really believe that is how a human brain works. So scientists are often referring to, yeah, we're mapping the brain and we're really close, another 40, 50 years and we can do it. I don't think with the current paradigm of modeling neural networks, we can really do what the human brain does. And it comes back to the model of context again, because you can never capture all the context, and we humans are really good at capturing context. So I don't think we can ever build enough sensors to really capture the context for a computer. So we could have trained the neural network to recognize the Rorschach test, and then he would have said, ceci n'est pas un Rorschach test, it's a digitized version of an ink stain on paper, or it would have recognized it as a Rorschach test, whatever. We could have trained it to do that. We could train computers at specific tasks, even if this specific task is quite hard. For example, the Watson case. If you give a computer the right context, you can train it to solve and outsmart people in a specific case. So I think there's a huge potential for Watson-like computers to deliver services to humans that help in creativity and all that. But I think the combination is really important. Okay. So we could say interpretation versus intelligence 2.0. So yeah, computers are better at humans in some points, but not always. Interpretation bots. I like music, I like records. This is a robot I built. Well, this is the output of a robot I built that will analyze record covers and come up with its own interpretation. That's my architect's background. Old pen plotters that were used for architect drawings. They're thrown on the garbage, but they're actually quite interesting robots. You can program them, and this robot will recognize a record cover by image, or you can just give it a title. Give me a cover of this cover. It will go online, look up the record, get all the metadata, scrape all possible data, then make some associations on it, and then it will come up with some shapes, and it will actually put credits on the. So here it says, for example, fingers from. This is the author of the drawing. So I correctly reference the author. So it's a Gesamtkunstwerk of how would you say that? But this is an interactive. Let me just see if I can show a bit the. Oh no, completely wrong. I wanted to show this. So we had the data, process, and interaction. So different ways of interacting. So it's always a combination of the data and process and interaction methods. I'm going to start with the simplest form. It's the egg cutter. That means the process is fixed, the data is fixed, and the result is fixed. You put an egg in the machine and you get a sliced egg. That's I haven't. The reason I show an egg cutter is because I didn't really do a project like that, so I couldn't really show you a relevant project. So I thought an egg cutter will do. It's a tool. It's a very interesting tool if you need to cut eggs, but it's not an instrument as a performative instrument that will aid you with creativity, unless you start using it in different ways than it was intended for, but let's not go there. So what if we fix the process and we make the data variable and then we apply some involutive genetic filtering? So This is a project I did for also with an artist where we took her body, a 3D scan of her body, and then started slicing it. So the input data was random, or not random, but well chosen. And we could do evolutions of it. So, but it's basically an involution because you return to the source. So after a couple of generations, it looks like this. And eventually, if you these are mapped all out in 3D. If you go to the center, then you get a small ball, the egg, so to say, where it all started. So it's a reverse genetic process. Okay. Another way of doing things is make the process variable and keep the data fixed. This gives a live result. I cannot really show it. It's an old project I did. It's called NetGlitch. At a hacker conference, I invited hackers to use a laptop to hack banks and whatnot and governments. But I would monitor their data. I would monitor their processes and see how they do it. The data was fixed in the way that it was mapped to sounds, and the sounds were then streamed. So we had a sonification of the process of a network attack. Just saying. But if you then take the process, make the process variable, the data variable, then you get a live result. That's, for example, live coding. Because in live coding, you can really alter the functions of the program while you're performing, as well as the data that is coming in. Here we're live coding with two people, so we both produce data, we both produce processes that alter the data. So it's a really mixed up version. So you could say that, well, it's infinity, right? So we get into the loop. So once you get here, I think you start outsmarting the computer. So it's 2 versus infinity if you can combine successfully computers and humans. All right. One note on randomness or random data, because sensing, oh yeah, that's cool. I have to read it from there, because designing computational system to structure performance-driven morphologies is just a randomly generated slide from the conference proceedings. So if I return, I can go to capturing mutual form to tell hybrid models, or oh yeah, farming hybrid development to structure asymptotic data. I could have tried and really explained this, but the point here is you can use random data to give you input and structure stories. So I wrote in the comments, explain this. The slide is called random slide. I don't know what I was supposed to explain, but maybe the tool I used is quite interesting. It's called Tracery. It's a free JavaScript library, and you can use it to generate, you can create grammars with it, and then use these grammars to create sentences, and then use these sentences to create stories. It's recursive, so you can continue with it all the time. And you can apply it to images or 3D shapes or anything you like. So random, it's quite important. Do you know the datasaurus? I'll wait for the animation to finish, because hopefully it returns to being a nice dinosaur. There we go. This is exactly, well, not exactly the same data, but it's rendered with a different plotting algorithm, but the same stats. So it's an Autodesk research paper. You should check it out. It's in the link here. I'll share the link later. But it marks the importance of how you visualize your data, but also how random can generate really different results, and if you adapt the process, then you can get basically whatever data you want, whatever output you want. So another example of random data is record covers I made here. It's 300 different record covers, and yeah, basically it's random data. I'll just, I don't hope it's not too loud. Yeah, that's the music that comes with it. So what we do is the structure of the music is analyzed and then plotted, but there's some random data added to it. Mainly the pens that are in the plotter are randomly chosen. The paper is either brown or white. You see it gives results that are like families and always different, and yeah, well, you should check it out. Okay, oh, wrong direction. So yeah, some more pictures. It's also done with a Roland pen plotter. They're really cool. If you find one, please give it to me. All right. In the last section, I want to talk about the interface. If you work on data together, you need to have a good interface. The humans and the bots need to be able to talk to each other. So humans do appreciation. Let them interact with the process and the data. Let humans change the course when they feel like it. I mean, the computer should not be the one to decide this looks good, this looks bad, this is we should continue with that. We've seen some talks where people had data models, and the data that would return was in the genre of this uses the least steel, this is the strongest structure, but still, let the humans decide on that if that's needed. But we've seen examples of that. Make sure you can bend the rules. If this is the algorithm, the bot is really good at running it. So let the bot do the number crunching, but let it follow your rules and harvest your well-planted data. Make sure the data is shown as much as possible and the processes are transparent, so you can understand what's going on in your data farming plant. On a last note, I think I want to show this. I haven't got anything to do with it. I just really like it. I like the interface. It's minimal, I know, but the visualization of the data is also the interface. So it's a synthesizer. It's a very specific tool. You have an envelope generator here. I can drag it and then it changes. I can do a stereo delay here, and if I drag this one, the left channel will have another delay. If I drag the right one, the right channel will have another delay, and it's immediately visualized here in the window how this works. But this is directly intuitive. It has a direct relation with the result that I'm hearing and I'm seeing. So we should design interfaces more like this. It's not perfect yet, but you should go for the intuitive data interface and display data as the interface. So if you're visualizing it, then you might as well make it interactive and make it the interface. For example, I wanted to connect with the systems you have in place, like the load placement or the number of segments in a truss. You could easily make that interactive by itself, just by removing one. The structure could reorganize just by double-clicking on one of the bars, for example, or dragging, or, I mean, it's not my field of expertise. I don't know what the variables are in that, but I think if you can display the data as the interface, then that's a great step ahead. So the goal is that tools become instruments, and now go and do some data morphogenesis. Thank you very much. You can find the slides here, and I'll put them on Twitter as well.